So today I'm going to deliver a lecture on direct numerical simulation, local discretization approach. My name is Faisal. I'm from Department of Mechanical Engineering, AMU Aligarh. So numerical simulation of turbulence doesn't use any turbulence models, captures the basic physics of fluids in simple flows. Numerical experiments can be unphysical and can be conceived by the researcher himself. It's a tool for fundamental research, giving most accurate results. It's computationally intensive and is able to resolve both large and small scales. It is used primarily for the identification and study of coherent structures. 80% of turbulent kinetic energy as it resides in wall-bounded turbulence. It is contained in these near-wall coherent structures, and primarily we intend to reduce this turbulent kinetic energy in order to bring about skin friction drag reduction, or we want to do enhancement of turbulent mixing, or we want to do reduction of heat exchange. So it has got strong applicative interest and with very high potential benefits. The governing equations are Newtonian fluids for incompressible and constant properties. The governing equations are three Navier-Stokes equation expressed in vector form as given in the slides over here, where we get the conservation of mass, del dot U equal to 0, conservation of momentum, as can be seen over here, and conservation of energy. Then we have the scales employed for non-dimensionalization. We got the length scale, we got the velocity scales, which makes use of friction velocity. We got the pressure scale, time scale, as well as the temperature scale. Here, the friction velocity is given by the expression as given in the slide. The non-dimensional form of the governing equations is mentioned over here. So conservation of mass, conservation of momentum. Now we'll get frictional Reynolds number as well as Richardson number, conservation of energy.
What's not working? It is
Still not going. So it's defined by non-dimensional numbers such as Reynolds number, Richardson number, and Prandtl number. The geometry of the physical domain can be seen from here, which involves basically a turbulent channel of length 2 pi, span-wise length pi, and wall normal height of 2 delta. And that's basically concerned with the stretching transformation that we have used in order to fit the grid over here. So the expressions can be seen from the slide. That's the stretched mesh in the wall normal direction. As you can see, there's a large proportion of finer mesh near to the wall, and that's the initial and boundary conditions that we have used in a simulation. So primarily the boundary conditions are for stationary solid surface, and these are no slip, no penetration conditions with periodic boundary conditions in the streamwise and spanwise direction. The SMAC algorithm has been used in order to solve the governing equations, and it's a two-step predictor-corrector algorithm with implicit handling of the diffusion and explicit discretization of the convective terms.